Hey, welcome back to our next Algebra 2 lesson. We're going to be solving rational equations today after we just take a minute and talk about something called undefined values. Now, undefined values are related to undefined fractions, which you might remember from previous grades, and it's related to the idea that we can never divide by zero. Solving rational equations is a bit of a doozy, but it combines a lot of stuff which you have mastered before. It combines factoring, it combines adding and subtracting rationals by finding the LCD, and more factoring at the end to solve them out. It might seem like a lot, but you guys got this. Without any further ado, let's take a look. We're going to start today by talking about undefined values. They are specifically values of x that make the denominator equal to 0. You might remember hearing that any fraction with the denominator of 0 is undefined. That's exactly this idea as well. Now we can find these by you just set the denominator equal to 0 and you solve for x. The numerator doesn't matter whatsoever here. The numerator can be the craziest looking thing in the world. It doesn't matter. Let's take a look at some examples. Number 1. What makes that value? What value of x makes the expression x plus 4 over x minus 3 undefined? I'm going to ignore the numerator altogether, and I'm just going to set the denominator equal to 0. Then I'm just going to solve. So 3 is the value that makes this expression undefined. That's it. We're done. Let's take a look at number 2. The expression x minus 3 over x plus 2 is undefined when the value of x is, same deal. I set my denominator equal to 0. I solve out. And I'm done. That x minus 2 is the value of x, which makes the expression x minus 3 over x plus 2 undefined. Now, this last one, the expression, I'm not reading that out, is undefined when x is, okay, that's a crazy numerator. The numerator doesn't matter. It's kind of just there to throw you off. I'm still just going to set this equal to 0 and solve. So that means I have negative 28, which means x equals negative 7. So this expression is undefined when x is equal to negative 7. Even though that numerator was crazy, we didn't need to worry about it when we're thinking about undefined values. Now, these look a bit more complicated, and they are. Our denominators have exponents in them. We need to factor to solve. That doesn't make a difference of what we need to do, though. I'm still just going to set, let's call this number 4, that equal to 0. You got two options here. I'm going to go with the factoring option. That means that it's x plus 2 and x minus 2 equals 0. We're going to need a bit more room here, which means I can say x plus 2 equals 0, x minus 2 equals 0. So x equals negative 2, and x equals positive 2. So this has two values that make this expression undefined. And you can check because if I'm just looking at the denominator, if I plug negative 2 into this, negative 2 squared is positive 4, which means 4 minus 4 would equal 0. Same thing if I plugged in positive 2. So let's take a look at the second one, or rather this fifth one. This is number 5. This expression is undefined when x is set it equal to 0. This is also going to be difference of perfect squares. It's not in standard form. The variable isn't leading. That's okay. This is just going to be equal to 3 minus x and 3 plus x equals 0. So that means I got 3 minus x equals 0, 3 plus x equals 0. I can say this is 3 equals x because I just added x to both sides. I can say this is negative 3 equals x because I just subtracted 3 from both sides. So this expression is undefined when x is equal to positive or negative 3. Last one we're going to do of these. Then you can head on over to Delta Math and do them. Just pause this video after this one. Not after this one because I got a trick to show you. This is undefined when, well, when x squared plus 2x minus 8 is equal to 0. That's a factors and sums. So it's going to be x plus 4, x minus 2 equals 0. So x plus 4 equals 0, x minus 2 equals 0, x equals negative 4, x equals positive 2. So these are the two values that make this expression, or rather this function, undefined. It doesn't matter that they said function here instead of expression, same deal. Now you can also find undefined values by using a graph and looking at what we call a vertical asymptote. It's just a line that the function approaches, but it never touches. And it might look like something like this. Suppose you had a graph that went la da da, whoosh, then this other one went whoosh. This value right here would be our vertical asymptote. And I'll show you how it looks on Desmos, as well as how to get a table on Desmos in a second. So I'm going to show you how to check this last one, number 6, using Desmos to see if these really are the undefined values. So to do that, we exit out of here. We go over to Desmos. I've already typed everything in, and you're going to get this graph. These graphs always tend to look extremely strange. I'm then going to type in my values, so that's going to be x equals -4, and I'm also going to have x equals 2. Now, you can take a look at where these are. Let's take a look at the -4 first. That value, the red graph is always going to get close to the value but never actually touch. So for instance, if I were to zoom in, let's look here. It looks like they're overlapping, but if I were to zoom in, there's still a difference between them. Same thing here if I'm looking at the green value. It looks like this green value at +2 overlaps the red graph down here. It doesn't. There's always a difference between them. It's a really small difference, but there's still a difference. And wherever you see one of these, what we call the vertical asymptotes, we typically write them with a dashed or a dotted line to show that they're not part of the function, but they're something the function is approaching, but will never actually hit. The Greek for asymptote is not falling together. And because it's undefined there, the function doesn't exist there, we can take a look at a table. So if I go here to Desmos, I've clicked that gear and I'm converting to table. At 2, it's undefined. There's simply nothing to report there. The graph does not exist there. The function doesn't exist there. And at -4, the same thing. It's undefined. So 2 ways to check where your undefined values are. Now, the fun part. We're going to solve rational equations. Now, you read your textbook, and you saw that there were 3 methods of doing it. We're going to focus on method 2 for this. Now, we're going to rewrite the equation without fractions. Fractions are annoying. First step is going to be to get rid of them. And to do this, we're going to multiply by the LCD, the lowest common denominator, which cancels out all the denominators. And this example below is what was from your textbook. We found the LCD, which in this case was 4. We multiplied both sides of the equation by it, and we went from this line, which had a bunch of fractions, to this line, where they're all gone, and all of a sudden we don't need to worry about them anymore. Let's take a look at how to do it. What's the solution set for this equation? Now, to find the LCD, remember from our last lesson, it needs to have factors from all the denominators. This is one factor, so it's going to have the x. We also have this as a factor, so it's going to be times x plus 3. X plus 3 is also here. We've underlined all the factors. We're good. You might be tempted to say, but wait a second. I already have an x underlined in blue. Why do I need to include this x in green? And the answer is, this x is not just multiplying something, it's adding to the 3. So it's a different factor than just the x. So I'm going to multiply everything by that. And now we're just going to cancel stuff out. That x and that x cancel. The x plus 3, the x plus 3 cancel. The x plus 3, the x plus 3 cancel. And I'm just going to rewrite everything with the things that did not cancel out. Cool. My next step is just going to be to simplify a little bit, combine some stuff together. So this is going to distribute. And then I just need to solve it out. So I'm going to I'm going to choose to move everything over to this side because that's going to give my x squared a nice positive coefficient. So I'm going to add 3x squared. I'm going to subtract 6. I know that's going to go over here. And I'm going to subtract 2x. I know that's going to be over here. That cancels, that cancels, that cancels. I get 0. This is going to be 4x squared minus 2x minus 6. Let's solve this one out. First, I'm going to take a GCF. Then I'm going to do grouping. I'm going to save a little bit of time. I did the grouping earlier. I'm just writing it out. And then we just set everything equal to 0 that can be equal to 0 and solve. So I do, well, 2x minus 3 equals 0. X plus 1 equals 0. That means x equals negative 1. 2x equals positive 3. X equals 3 over 2. So this one was a bit wonky, but it just goes to show you that as soon as we multiply by the LCD in this step, it's the same as things that we have seen in the past. Now, there's a catch. When we multiply both sides by a variable like this, we're opening ourselves to the possibility of extraneous solutions. They're extra. Now, it's a fancy word for saying that they look like they make the equation true, but if you check the equation, it reveals that they don't make it true. They're extra answers which popped up in our process. And here is just what we got. So in this one, this is just what we had. And we want to see if these two are extraneous solutions. How do we check to see if these are extraneous solutions? Well, I can just plug these into my denominator and see if they make anything equal to 0. And I can just do that in a simple little check. So I'm going to do 2 over negative 1 minus 3 times negative 1 over negative 1 plus 3 equals negative 1 over negative 1 plus 3. And if I simplify this, this is just going to be negative 2. This is going to be minus negative 3 over 2 is equal to negative 1 over 2. I can plug all of this into a calculator, and I'm going to wind up with this side being negative 1/2 equals negative 1/2. That works. So that means this answer that we plugged in, the negative 1, is not an extraneous solution. It totally works. We can do the same thing with the fraction. The same deal. So this actually is going to equal to 1/2 over 1/2. It works. So that means that x also equals 3 over 2. And we can check this in Desmos as well by looking at a graph. So what is the solution set of this one? Same deal. We're going to do the LCD, and that's going to have to equal, I see this and this as factors. I see this as a second factor. I always just like putting the variable by itself first. You don't have to. That's perfectly up to you. So then, I'm just going to rewrite everything and multiply it through by my LCD. Cancel some stuff out. 3x plus 1, 3x plus 1. X, x. 3x plus 1, 3x plus 1. And then I'm just going to rewrite it. This is x times 2 is equal to 3x plus 1 times 1. Well, that's going to be nice. Then we got x times 6x. Cool, so we're going to rewrite it a little bit. And then I'm going to move everything over to this side, because right here, this is a negative coefficient to an x squared. That's just going to make my life annoying. I don't want to make my life annoying. So if I can make it positive, cool. So I'm just going to add 6x squared, subtract 1, subtract 3x. So subtract 3x, subtract 1, add 6x squared. I'm going to wind up with 6x squared. 2 minus 3 is going to be negative 1x. Minus 1 is equal to 0. We solve this one out, we're good to go. So, factor by grouping, a times c is equal to 6 times negative 1 is equal to negative 6. The factors of negative 6 that add up to negative 3 are going to be 6x squared minus 3x plus 2x minus 1 equals 0. So that means I have a 3x times 2x minus 1 plus a 1 times 2x minus 1, which means that my factors are 3x plus 1 and 2x minus 1 equals 0. So solve them both out. This is going to be 3x equals negative 1, x equals negative 1/3, 2x equals 1, x equals a half. And let's check this using a slightly different method. We're going to graph it out. So what we're going to do is solve or check this for extraneous solutions using Desmos. And I'm going to first graph out this as one equation and this as a second, and I'm going to look for where those intersect. Specifically, I'm just looking for these two values down here at the bottom. X is a negative third and x is a half. So I've already gone and plugged them into Desmos. They look super weird. One is the green that you see, the other is the purple. And I want to see if they intersect at x equals negative a third and x equals positive a half. So I can turn this on, and we see right here, that's a point where the purple and the green intersect. So that means that this one checks out. X equals 1/2 is a solution. I can check this one as well. And I want to see if these two are going to intersect. You see how they're always really close? Like no matter where we go, they just keep getting closer. Well, that's telling us that it's not going to work for us. And we can check this algebraically, because if I plugged negative 1/3 in for this denominator, that'd be 3 times negative 1/3, which equals negative 1, and then negative 1 plus 1. It gives 0 as the denominator, which does not work. It would be undefined. So in this, the only solution that we have that works is this. The other one doesn't work by our check, so you can just cross it out. Just write checked by graphic. That totally works. You might be intimidated by the problems we just saw. It looks like a lot. However, not every one of them turns into a quadratic. In fact, the first solving equations portion of your homework will make them into linear equations. A lot easier to solve. And they won't always need factor by grouping either. You know a bunch of different ways that you can solve out equations. Also, you know that you can check your equations by graphing in Desmos. It's really, really helpful to do, and I encourage you to do it. So, head on over, do that delta math, then do the summary. We don't have a reading for tomorrow. After that, you're good to go. Just check with everything. Have a great day, folks.